So far in 2.4, we've learned the basics of linear programming. So what we're going to do now is we are going to actually apply the linear programming to real-world problems. This usually has to do with finding the maximum or minimum profit or cost for a certain situation. So the different steps we're going to use, number one is we're going to identify the variables that will represent x and y. So I just pretty much always use x and y to represent the two different aspects. Then identify the constraints and write them as inequalities. So we're going to break down the problem and write down different equations or inequalities that are going to work for our problem. Number three, we're going to graph the constraints. So we're going to do this on desmos.com/calculator. Spelling is hard. Desmos.com. And then we're going to find the vertex that maximizes or minimizes the objective function. So that's the one that's going to have to do with the money. This plays into the vertex principle of linear programming. So that says if there's a max or minimum value of the objective function, it is at one of the vertices of the feasible region. So we're going to look at that on Desmos and check out the shaded region. So we'll see that in action in a bit. So the first thing I would do is read through the problem. So this says a parking lot attendant is trying to determine the number of cars and buses to allow into the parking lot. The area of the parking lot is 600 square meters. A car requires 6 square meters and a bus requires 30 square meters. The attendant can handle only 60 vehicles. If a car is charged $2.50 and a bus $7.50, how many of each should be accepted to maximize the profit? So we're looking for like the biggest profit. So our first step is to identify the variables. So this whole problem has to do with cars and buses. So our variables, we're going to have x be the cars. If you don't like x and y, you can use something else, but on Desmos, you'll need x and y, I believe, because we've got an x-axis and a y-axis. Next, we're going to do our constraints. So for our constraints, it says the area of the parking lot is 600 square meters. And then a car requires 6 square meters, a bus requires 30 square meters. So all of those have to do with square meters, so they're going to go in one equation together. So a car was the 6, so 6 will go with the x. A bus is 30, so 30 will go with the y. And then the total square meters is 600. Since our parking lot is 600 square meters and it can't be bigger than that, when we add together the cars and the buses, it should be less than or equal to 600, so it can't go bigger than that. Next, we're going to look at the next sentence. The attendant can handle only 60 vehicles. So that means combined X's and buses, our total has to be 60 or less. So if you add together your cars and your buses, that should be less than or equal to 60 vehicles. Finally, these are two ones that aren't mentioned in the equation, but you can't have negative cars or negative buses. So to add that constraint in, you want your cars, so X, to be greater than or equal to 0, and your Y to be greater than or equal to 0. So we're doing this because we don't want a negative. So we don't want negative vehicles. So unless the equation or the problem tells you differently, you'll probably want to add in those two constraints whenever you're writing word problems. Finally, we've got our money. So a car is charged $2.50 and a bus is $7.50. So we are working for profit. So we're trying to charge people. So its profit is going to equal $2.50 per car and $7.50 per bus. And that's what's going to go in our table for profit. We're going to have 250x plus 750y. So to fill out this table, we're going to graph these 4 equations on Desmos. So you're going to go to Desmos and plug all of these in. So I've already graphed them. So here they are. A reminder on Desmos, this little button at the bottom, you can click it to get the keypad so that you can do the inequalities, so like the less than or equal to's. So when you graph them, it may be kind of zoomed in. So you can use your fingers to zoom out, or you can use these arrows to zoom out on the side. So what our goal is to find the area that includes all 4 shadings. So we've got 4 different colors, and it has to be shaded by all of them. So hopefully you can see this area in the middle. It's got a 4-sided shape. I've got 4 corners of the shape. And if you click on them on Desmos, they should give you what the vertices are. So those 4 corners include all 4 colors. So those are going to be our vertices. So we're going to write those down in the table in our notes. So those 4 points were 0, 0, 0, 20, 60, 0, and 50, 10. So once you have the points, we plug them into our equation. So it'll be 2.5 times 0 plus 7.5 times 0. That equals 0. Then 2.5 times 0 plus 7.5 times 20. And that equals $150. Then 250 times 60 plus 7.5 times 0. That equals 150 again. And then 250 times 50 plus 750 times 10. And that equals 200. So our goal here was to find the maximum profit. So if I look at all these profits that we've earned, the biggest one was 200. And the point that went for that was the 50, 10. So 50 is the X, so that means there were 50 cars, and 10 buses would give us our maximum profit of $200. All right, that is the first problem. Then I want you guys to cross off problem number 2. I think it's pretty confusing. We're not going to do that one. And then we'll jump to question number 3. So first thing we're going to do, read the problem. A construction company is building small stores and large stores on a 16,000 square foot vacant lot. Their small stores take up 1,000 square feet. Their large stores take up 4,000 square feet. The city wants there to be at least 7 total stores to build on the lot. If a small store costs $15,000 to build and a large store costs $35,000 to build, what combination of small stores and large stores would minimize the total cost? All right, so our variables, we've got an X and a Y. I'm going to call X my small stores and Y my large stores. So when we start working through this, we've got to do constraints. So they've told us that we've got a 16,000 square foot vacant lot, and the small stores take up 1,000 square feet. The large stores take up 4,000 square feet. So all of those numbers have to do with square feet, so they're going to go in the equation together. So we'll have 1,000, and then that goes with small, so X, plus 4,000 goes with Y. And then the total is 16,000. So we can't be bigger than 16,000 because that's the size of the lot, so it's going to be less than or equal to 16,000. Next sentence, the city wants there to be at least 7 total stores to be built on the lot. So adding small and large together, so X plus Y should be at least 7. So at least means greater than or equal to. So whenever you see the word at least, it's going to be greater than or equal to. So greater than or equal to 7. And then once again, we don't want to have negative stores. So X should be greater than or equal to 0, and Y should be greater than or equal to 0. Finally, we'll do our money. So costs, small store costs 15,000, large store costs 35. So instead of profit, now we're doing cost. So cost equals 15,000 X plus 35,000 Y. And that's what's going to go in our table. All right, our last step is to graph these and fill in our table. So I graphed them ahead of time. So they should be not there. Here we go. All right, so when you zoom out, this one was tricky for me the first time. I first kind of saw like the area over by the x-axis and the y-axis, like in the corner, but that doesn't include the green shading for me. So it's really going to be this triangle. So this triangle with those 3 vertices, that includes all 4 colors. So that includes my purple, red, black, and green. So those are going to be the 3 points that I stick in my table. So in the table, we've got 7, 0 is 1 vertice. We've got 4, 3, and we've got 16, 0. We're going to plug in all those points to the equation. Honestly, anything times 0 is 0. So if you want to skip writing like 0 steps, like the 35,000 times 0, you totally could skip that because it equals 0. So if you didn't want to write here 35,000 times 0, you know it's going to equal 0. All right, so when you plug those all into your calculator, the first one equals 105,000. Second one equals 165,000. And the last one is 240,000. And all those are dollars. So our goal on this problem is wanted us to minimize the cost. So minimizing is the smallest. So this 105,000 is the smallest, and that's the 0.70. So that means for our answer, we're going to have 7 small stores, because 7 is the x, and 0 large stores, because 0 is the y. And that will be a minimum cost of $105,000. All right, those are 2 examples of how to do linear programming in real life. Hopefully this will help you with the homework.